This is the second video about our general gas laws. And our next gas law involves looking at the relationship between the volume and the amount of a gas. The previous two gas laws kept the number of moles, the quantity of the gas, constant. And this is the first one that's actually going to look at what happens when we change the amount. So one of the ways to first start thinking about a gas law like this is to think about what happens to a balloon when you're blowing in it. Now, when you blow a little bit into the balloon, you put a little bit of air in and it, gets a little larger. And then as you blow more air in, then it gets a little larger, and you blow more air in and it gets a little larger, and so on and so forth. Now, this isn't a perfect comparison because the pressure in a balloon actually is not kept constant. And in the gas law here, we are keeping the pressure and the temperature constant. But a balloon is also not, it's not quite the same kind of material because it's all stretchy and stuff. So it'd be more sort of like inflating, I don't know, a plastic grocery bag or something like that. So we can generally think about the fact that the volume taken up by the gas is going to increase as we add more material. So volume should increase as we add more gas. And that is exactly what happens. So just like with volume and temperature, where the volume increased as we increase the temperature, the volume is proportional to the amount of the gas as well. So another way for us to write this would be that volume is equal to the number of moles times a constant. And C in this case is also just another proportionality constant. So just like we had V1 over T1 is equal to V2 over T2 with our previous direct relationship, if we divide out the number of moles here, you can see that we also have V1 over N1 would be equal to the constant. And for some other volume and number of moles of gas, this would still be true. The same proportionality constant still works, which means that we can talk about relating the number of moles of gas to the volume in a similar kind of setup. So this is called Avogadro's law, and it's the same Avogadro of Avogadro's number. And this one he did actually explore. Avogadro's number, he didn't come up with the total number of moles, but this was the property that he came up with, that the proportional size of the amount of space taken up by the gas relates to the amount of the gas that is present. So our next gas law, which is the last of our four gas laws, is looking into the relationship of pressure and temperature. And of course, as usual, we are keeping our other two constants, or our other two variables, constant. So we have one size of a container. That would be what keeping volume constant means. So we can pressurize the gas and we can raise the temperature of the gas. Those are the two things that we can do. But instead, what we're really looking at is what happens to the pressure as the temperature increases. That's what this is exploring. So remember what happened with the volume as we increased the temperature. The volume increased, and we know that if a gas is taking up more space when we increase the temperature, now we're not allowing it to expand. And so this means that we should expect that the pressure should increase when the temperature increases. So in other words, we have another direct relationship, just like the last one, that pressure is proportional to temperature, or we can write it again as an equivalence. and look at pressure being equal to the temperature times some constant. Oh, I forgot to graph this one. I'll graph it right down here. So when we look at relationships that are like this, pressure versus temperature, we're going to have a direct relationship. So this is a linear function. And since I forgot to graph this one up here, I'll do this one too. So we also have a linear function between the volume and the number of moles of gas. And these probably don't have the same slope, but they both are linear. Maybe I will make this one a little more extreme. That way we can really see they don't have the same slope. Okay, so just like the relationship we found for Avogadro's law, we have that our pressure would be equal to the temperature multiplied by a constant, which means that if we divide out the temperature, then this is just equal to the constant. And this would also be true for some other pressure temperature combination. So if here is where my P1 and T1 are, then the D, that's the slope of this line, right? And so if I go to some other pressure temperature combination, P2, T2, then the slope of the line is the same in both of these places, and so this equivalence still works. So we can solve for these relationships in exactly the same way. This relationship is another named law. It's called Amonton's law. And the interesting thing is that although I see people mentioning Charles' law and Boyle's law a lot, I don't actually see people talking about Amonton's law and Avogadro's law a lot. And I just wanted you to know that you do not need to remember the names. I will never ask you about which one has, is related to which name. I might ask you what the relationship is between pressure and temperature. And so you should be able to remember something like this. But I won't ask you, what's Amonton's law? I mean, maybe on a worksheet where you can look it up, but not on a quiz or something. Okay, so now that we have two more gas laws, let's try some practice problems with these ones. Structurally, they're really going to look very much like the previous ones did, where we're just solving for one unknown. So let's look at one. All right, if a sample of gas at 350 degrees Kelvin has pressure equal to 3.79 bar. Oh, by the way, I might not always give you the units in the same thing, so you may have to convert units. In these sample problems, I'm not going to. I'm just going to leave the units the same, but I might leave like one temperature in Celsius, or I might have bar pressure and millimeters of mercury, so you would have to convert something. So just kind of keep that in mind. So if we have this sample of gas at 350 degrees, has a pressure of 3.79 bar, and we increase the temperature to 450 degrees, what is the new pressure? All right, so we can see again that this uses Amonton's law. We have a temperature that is related to a pressure, and then we have a new temperature, and then we need to calculate a new pressure. So make sure that you pair things up appropriately. So 3.79 bar goes with 350 Kelvin. And I'll put decimal places here so we know we can keep 3 decimal places. And we're solving for P2 divided by 450 Kelvin. So rearrange that. And if we plug that in, we should get 4.87 bar. Oh yeah, we forgot to predict what was going to happen. So remember, we had a gas at a particular temperature and pressure, and then we increased the temperature, and we do expect the pressure to increase, and that's what it did. I'll try and remember to predict for the next one. Okay, so now let's look at another practice problem. So we can say if a gas has volume of 5.26 liters and contains 1.72 moles of gas, how many moles of gas should be added to increase the volume to 10.53 liters? Okay, so we know our general relationship is a direct relationship. So if we want to increase the volume, we need to increase the number of moles. And that's actually even part of the problem, right? I said how many moles of gas should be added. So I've already told you that our number of moles are going to increase. So one thing you might notice here is actually the numbers that I picked. I accidentally picked a volume that was twice as big as my previous volume. And since this is a linear relationship, we expect that the number of moles is probably going to be twice as big. So let's look at our equation here for Avogadro's law. So what do we have? We have a volume and a number of moles, and we have a new volume, and then we need to calculate a new number of moles. And I actually am asking you what the difference between the moles is. How many moles should be added? So let's see what happens. So it means that we're solving for this guy down here, which means we've got a little bit more rearranging to do. So I am going to multiply this number of moles over here, and then I'm going to divide out everything else to get it on one side by itself. But I'll show all those steps there just in case. So this is what happens if I multiply the n over to the other side. Now I need to divide out my volume 1 and multiply out my n1. So that's going to rearrange to n2 is equal to v2. This guy's going to come over here, and this volume is going to be in the denominator. So n2 is going to be my new volume, 10.52 liters, multiplied by my original moles, 1.72 moles, divided by 5.26 liters. So this gets me 3.44 moles as my total number of moles. But my question wasn't, what's my new total moles? My question was, how many moles of gas should be added? So that means I need to take 3.44 moles, which is my new moles, subtract 1.72 moles, and as I said, this turns out to be double, right? So I have to add the same amount of moles that I had before so that we get to having double the amount of moles. So you should be pretty comfortable here. We now have talked about proportionality of several different things. We've talked about the relationship between pressure and volume, volume and temperature, pressure and temperature, volume and moles. And in our next video, we're going to talk about putting all of these together in one equation, which is mostly what we're going to use.